In this video, we're going to talk about Faraday's law and Lenz's law. And the first thing we need to do is talk about magnetic flux. So magnetic flux is just the amount of magnetic field passing through an object. And you can change the magnetic flux by either, if you turned on a solenoid, it would create a magnetic field. So if you had a current loop above the solenoid, suddenly there'd be magnetic field going through it, so the magnetic flux would change. You could also change the magnetic flux by moving a magnet closer or further away from something, because that's going to increase the strength of the magnetic field or decrease the strength of the magnetic field. You can also do it by increasing the area that something has so that more magnetic field can go through it, or by turning it so that more magnetic field is exposed to it. And you can visualize it just as magnetic field lines and thinking about how many can go through an object. So Faraday's law is that if the magnetic flux through a circuit changes, then there will be a current produced in that circuit. So the classic example is if you have a bar magnet and you move it closer to a current loop. Okay, a current loop is a circuit. The magnetic flux through that circuit is going to change because the magnetic field is going to get stronger, and that makes a current in the current loop, and that's really quite weird. And Lenz's law tells us the direction of that current, and Lenz's law states that the direction of the induced current, right, the current that's produced from the changing magnetic flux, is such that the magnetic field it generates opposes the change in magnetic flux. Another way to think about that is the magnetic flux will be the change in magnetic flux will be opposed by the induced current. And these examples here in pictures A, B, C, and D are very illustrative. So if the north side of a magnet is moved closer to a current loop, there will be a current, and the current will go counterclockwise. And that's because that's going to make the north side of this current loop close to the north side of this bar magnet. And so we're bringing the magnet down, it makes a current, the current makes this the north side, and suddenly there's a repulsive force now that we have to overcome and pushing the magnet down. In picture B, the north side is moving away, so the current that's induced is going to be clockwise, and that's going to make the south side on the top here. And that's going to attract the north side of the magnet, making it harder to pull it away. In picture C, we have a south side coming closer. So to oppose that motion, the south side would have to be on top of the current loop, and the south will repel, making it harder for us to pull it down. That makes the current go clockwise. And lastly, if the south is moved away, the north side has to be on top of the current loop to attract the south side of the magnet to make it harder for us to pull away. And to do that, the current would have to go counterclockwise. And so one way to think about it is whatever is going to make it harder to keep changing the magnetic flux, which is us moving this magnet back and forth, that's the direction that the current will be induced. And that stems from a conservation of energy argument. If it went the other way, say here, and the south side were on top and the north side were on the bottom, the magnet would be attracted to the current loop. So the magnetic flux would keep changing, and I wouldn't have to do anything. And suddenly we would get energy through this current loop, through current. And you just can't get energy for nothing. So now, because the north side appears here, I have to spend my energy to push it down. And that energy that I spend is the energy that is gained in the current loop through current. So another way to change magnetic flux is if I had this circuit here and I just pulled this side out, I would be making this current loop bigger, so more magnetic field can go through, so the magnetic flux is changing. That will induce a current in a generator. So this is how we power our society. It's just like a DC motor, but you're turning it, and as it turns, more magnetic field can go through now, and less and less and less, and now more and more and more, and that will create a current. And that's how we generate power. And the loop is turned by steam or